Hello everyone, my name is Zhang and I am from National University of Defense Technology. I am glad to share my paper Automatic Exploitable Heap Layout Generation for Heap Overflows through Manipulation Distance Guided Fuzzing. As we all know, heap overflows are becoming one of the most popular threats to software. In order to turn a heap overflow POC to an exploit, one needs to construct a specific heap layout, which is known as heap layout manipulation. Previous researchers have proposed some automatic heap layout manipulation methods. However, this work only works well on interpreters or kernels because they depend on explicit heap primitives. For example, defining a variable by string repeat with size x in PHP can easily trigger malloc x. However, general-purpose programs like image parsers, executable parsers, are lack of such primitives, and the side effect introduced by chunk split and merge makes layout manipulation more complicated. This is an example general-purpose code that contains a heap overflow vulnerability. The code processes two types of optional information if needed. This procession triggers some heap operations. The POC to trigger the vulnerability is quite simple. It does not need any optional information. The epoch, which can lead to an exploited state, is shown as this. It contains both entry and file information, and the final exploitable layout is shown as LM file here, where C file is placed right after pure data, and overflowed data corrupts the pointers in C file, which can be used to construct an arbitrary write or read. It is difficult to extract precious heap primitives. For example, the number of times that M4 executes depends on the logic in precise form entries, which is difficult to model. However, without the support of heap primitives, we can directly transform the initial POC to epoch by manipulation distance guided fuzzing. To achieve this, we need to deal with the following three challenges. The first is how to specify a desired exploitable layout. Previous work flexibly specify a victim object as their input. However, the victim object are highly dependent on the program execution logic in general-purpose programs. For example, in this code, C file is created only when the input contains the optional file information block. The second challenge is how to improve the fuzzing efficiency. This contains two problems. One is how to locate the program input that controls the heap operations. The other one is how to define a more fine-grained distance other than previous work to direct the searching directions. The last challenge is how to model the side effects brought from complex heap behaviors such as trunk split merge and early occupation so as to preciously control the manipulation. Here, early occupation means the target trunk is early occupied by an allocation that executes before the target allocation operation. In order to deal with these three challenges, we propose scatter, and its high-level framework is shown in this picture. Victim object identification identifies partitional victim objects from source code that can be used for corruption through static analysis and inserts extra instrumentation code to obtain victim objects at runtime. The victim object information is defined as 3 tuple, which contains the allocation index, sensitive ID, and the runtime allocation address. In order to find which input control heap layout, we first extract multiple heap operations whose parameters or execution times can be affected by input. This is achieved by constructing the layout dependency graph LDG. For example, this figure here shows the LDG of the example code mentioned before. We can see that both M1 and F1 are multiple operations. Then we use a lightweight mutate check strategy to locate the input bytes. Unlike previous work that defines the distance as a gap between two objects' location, for a free chunk C who is suitable for the vulnerable object to overflow a victim object, we define the manipulation distance tau d as this. We define the manipulation tau d as this. By reducing the tau d to 0, we can remove all the free chunks whose position index is before chunk C in C's free list. However, the chunk split merge mechanism in modern heap managers affects the calculation of tau d. We update the manipulation distance according to the different behaviors. For example, suppose a target chunk locates in free list Lx, and for free operation free C, which C size is y. If free C merges one chunk in Lx and y is not equal to x, then this free operation is treated as an allocation operation, and we increase NA by 1 when calculating the tau d. Even though tau d can successfully reduce to 0, the early occupation problem still leads to the manipulation to fail. To deal with this, we introduce overflow factor, which depicts the change of target free list. That this denotes the accumulated changes of LC until sigma theta. The position index of chunk C is updated as this value. If this value is negative, it means the chunk C is early occupied. We get all negative values of this and find the maximum absolution value as the final overflow factor. After defining the distance, we leverage distance-guided fuzzing to find the final epochs. The first problem with fuzzing is how to determine a mutated epoch triggers with the same vulnerability as the initial epoch does. Previous work depends on ASIN, but it may change the layout. So we disabled ASIN and implemented our own method to check whether the epochs trigger the same bug. The other problem is which epochs deserve higher priorities to fuzz and how much mutation energy should be assigned. As shown in this figure, we proposed a greedy and a multiple level scheduling strategy whose top choice is the seeds with shorter distance. If all the heap-related metrics are explored, then we use a traditional code coverage as the last schedule metric. In order to evaluate our method, we select 27 heap overflows vulnerabilities in 10 real-world general-purpose programs as our benchmark. The input types include executable files, command line arguments, images, and raw text files. Here is general-purpose programs. The epoch generation result is shown in this table. Scatter successfully generated 126 epochs in 18 vulnerabilities. The failure reasons can be grouped in these 4 reasons. We also compare the scatter with other state-of-the-art methods. The results are shown in this table. Scatter generated the highest number of epochs among all the tools. We also compared the time consumption performance with other tools. The results are shown in this figure. We can see from this figure that the average time to generate an epoch for scatter is around 1 hour, and the scatter shows a shorter and a more stable time consumption when generating epochs. Okay, in this paper, we propose scatter, which generates exploitable heap layouts for heap overflows of general-purpose programs by manipulation distance-guided fuzzing. Even though we have made some progress in general-purpose programs' automatic heap layout manipulation, our method still has some limitations when dealing with non-glibc heap managers, customized heap managers, and multiple thread programs. Thank you. Any questions?